One of the challenges with dealing with fields is that they're hard to look at. In this last example, I just picked a bunch of random points and drew the vectors, and you kind of get an idea of what's going on, but how did I know where to draw those points, or how many should I draw to really get the full picture? Thankfully, we have some tools available to us to visualize fields that make this easier. The two big ones that we're going to look at are streamlines and streaklines, and we'll talk about path lines as well. So streamline we've already talked about. We said that that is a line that is everywhere tangent to the velocity field. And that's super useful for analytical work, things like Bernoulli. A streak line is kind of the experimental equivalent of that, and they're really useful in, say, wind tunnels and things like that. Anywhere that you've seen like smoke flowing over a car or whatever in a wind tunnel, that's not actually a streamline, it's a streak line. So let's get into the difference here, but first let's get more precise on what a streamline is. So a streamline is everywhere tangent to the velocity field. What's that mean? Well, it means that if at a point in our field we have a velocity vector that looks like this, v, right, it has two components to it. It has the horizontal component, which we've been calling u, and the vertical component, which we've been calling v. The streamline is tangent to this, which means it moves in the same direction as v, and so we can play a little similar triangles game here just to make this easy to visualize, which says that our dx and our dy on our streamline are in the same direction as u and v. In other words, we can write dy by dx, the slope of our streamline at this point, is equal to the velocity v over the velocity component u. And so this is actually the formal definition of a streamline, because what you can do with this is you can integrate it to get the equation of the streamline. Integrate to get the equation of the streamline.